Hey everyone, it's me again. I know you probably missed me. I miss teaching math. I miss being here. I love doing this stuff. I'm like full of energy today. I got little to no sleep, but caffeine is definitely on my side tonight. So, as always, it is Math Wednesday with the Learning Liaison, and today you have your lovely star host, Pryia. Today is brought to you by lots of pre-calculus and trigonometry. I know, my favorite topic. I don't know what it is about me lately, but I've really just been loving that stuff. So let's go ahead and jump into this. Like always, I have the chat open. So anybody that needs any questions, you know what to do, drop it in the chat. Ask any questions. I can always go back if I have moved forward, and I'm here to help you, right? So if you don't ask questions, I don't know if you need help. So help me help you in any way possible. Question 1, like I said, today is brought to you by Pre-Calculus. There's a high school college question, right? And the question simply reads, what is the radian measure of an 81-degree angle? So first things first is you have to know what they're even talking about. Well, we know that this is a degree. My circle didn't come out so great, so let's try that again. We know that this is a degree. We know that our calculator has two modes. It has radians and it has degrees. And if you're in the wrong mode, you won't be able to do this. And some of you aren't provided a calculator that actually can do this for you, right? So let's talk quick about just something that we can do. This is definitely something that we don't need a calculator for. We can do this by hand. And does anybody by chance know how to do it by hand? I promise it's very simple. There is one small thing that you need to know. That small thing, ladies and gentlemen, is pi over 180 degrees. So when we are going from degrees to radians, let's take some notes really quick before we answer the question. Let's go off to the side. So when we are going from degrees to radians, we're going to take our degree, I'm going to write it in words, and we're going to multiply it by pi over 180 degrees. And that will give us an answer in radians. And very similar to if we're going from radians to degrees, can somebody take a guess as to what we're going to multiply by? I will tell you it's not going to be the exact same thing. It's going to be close to, but not the same thing. We're going to multiply by the reciprocal. Does reciprocal sound familiar? Some of you are going, I don't know what a reciprocal is. That's okay. Reciprocal means to take a fraction and you flip it, right? So we're taking the flipped version of the fraction, that is a non-technical term, and the technical term is called the reciprocal. So we're going to have 180 degrees over pi, which does make sense, which we will do in a bonus question that I have written out. And what you're going to end up with is degrees. So now that we know all this lovely information, let's take the information that we need and let's apply it. I'm in a pink mood today. Let's apply it to the question. So it says the radian measure. So our answer choices kind of gave it away. We knew that we were going to do something with pi because all of our answers have pi in them. So what we now have to do is apply that rule that we just talked about. So we have 81 degrees, and we're going to multiply it by what? Pi over 180. Okay, so some of you are looking at it going, well, I don't know how to do that, and that's okay. There's a simple way to do this, I promise, right? Any number without a denominator is always over what? Any number without a denominator is always over 1. I should hear you all the way over here in New York. 1. You should be yelling it loud enough for me to hear. Any number without a denominator is always over 1. So that makes multiplying a lot easier because now we can multiply these two fractions with no problem. So I'm going to set them up, line them up so you can see it. And what we do here is we multiply the numerators together and we multiply the denominators together. So let's multiply our numerator. We're going to get 81 pi. We leave pi as pi because the answer choices told us to. And we're going to multiply 1 times 180, and we're going to get 180. Well, that's not an answer choice. So that tells us that we know that this is definitely reducible, right? So now we're think. What number goes into 81 and 180? Can somebody tell me a number that goes into 81 and 180? I'm really hoping you said 9. And if you didn't see 9, you can try small numbers like 2 or 3, right? And if you notice that 2 or 3 still gives you a fraction that you can reduce again, then you reduce again. But the number that we're looking for is 9. Great job. Thank you. So now we're going to divide 9 into 81, and 9 goes into 81 9 times. Keep your pi. And 9 goes into 180 how many times? Well, I know that 9 goes into 18 twice, right? So I'm going to take my 2, and I'm going to bring my 0 with it, and I'm going to have 9 pi over 20. And now you're going to think about what numbers go into 9, and that's really only 3. And you're going to think about what number, or 9, and you're going to think about what numbers go into 20, and that's not 3, and that's not 9. So at this point, we are at our ending point for reducing this, and our answer here is going to be B. Winner, winner, chicken dinner. I'm back with that phrase. I know, I've missed it. All right, you know the deal. If you have a question, where do you put it? Put it in the chat, and if I see it, I'll come back to it. Ready, set, moving forward. So like I said, I gave you some bonus questions today. So here are 4 questions, right? So obviously the degrees, well, let me not say obviously because it may not be obvious. The degrees are going to go to radians. Those are the first top 2. These are going to be degrees to radians. And the bottom 2 are going to be, not put lines because now it starts to look like it's another fraction. These 2 are going to be radians to degrees. Elementary math problems. I do have, at the end, I have some algebra. And algebra is, when you say elementary math, can you give me the name of the exam that you're taking? All right. That should have given you guys enough time to solve these problems. Are you guys done yet? You're probably sitting there going, okay, here she goes. Want me off the caffeine, but the caffeine's got me going today, so let's keep going with it. Remember, any number that doesn't have a denominator is always over the number 1. Okay, so really quick side note, for the subject area K through 6, I only have 1.5 problems that are related to that today. We're definitely doing a little bit more higher math today. So 36, that's degrees. We want to go to radians. What do we need to do? Multiply by pi over 180. And remember, any number without a denominator is always over the number 1. All right, so we're going to multiply our numerators together, and we're going to get 36 pi. We're going to multiply our denominators together, and we're going to get 180. And that is reducible. What is the number that we're going to reduce them by? 9. We're going to do 9 again. I know, I was just in a 9 kind of mood. So 9 goes into 36 4 times, keep our pi. And 9 goes into 180 20 times. Ooh, look at that. We can do it again. So 9 wasn't the smallest number. It actually was 36. But what I did was I showed you that if you get to a place where you have to reduce again, that's okay. Just do it again. Now we're going to divide by 4. 4 goes into 4 one time, and we're going to be left with pi in the numerator. 4 goes into 25 times, and our answer here is pi over 5. It's not too bad, right? Some simple math, but keeps your brain going. Now we have 225 over 1 times pi over 180. All right, so here we go. We're multiplying 225 pi over 180. And what do we do from there? We kind of stare at it and we go, well, I know that there is a number that will help me, but I just don't know what that large number is. So remember, we always talk about you can do smaller numbers to help you get to where you need to be, right? So the smaller number here that we're going to use is going to be 5. I know that 5 is a good number because 225, 5 is divisible by 5, so that's a good number to use. And zeros, numbers that end in 0, are also divisible by 5. So I'm going to use that little trick. And when I divide by 5, I'm going to get 45 pi over 36. And then you look at it and you go, oh, that's numbers that I definitely can reduce, again. And that number is my, seems to be favorite number tonight, which is 9. So we reduce it again by 9. And if you get what I get, we're all on the same page. 5 pi over 4. Winner, winner, chicken dinner. All right, so now let's go ahead and change some radians to degrees. We haven't done that as of yet, so this would be a good chance to do it. So remember we talked about using the reciprocal, right? So instead of using pi over 180, we're going to use 180 over pi. And the great thing about that is it's going to eliminate. So I'm using these air quotes because it doesn't really go anywhere. It transfers into something else, right? Kind of like the whole energy is nor created, not created or destroyed kind of thing, right? It's just transitioned into something else. So let's look at what that would be. We have 13 pi over 6. Remember, we're going to multiply that by the reciprocal of pi over 180, and that's going to be 180 over pi. You can write these with parentheses. You can write them with this little dot multiplication. It's whatever makes you comfortable, right? So you have two options here. Before moving forward, you can reduce. Remember, you can reduce numerators and denominators, but you cannot reduce numerators to numerators or denominators to denominators. So if I wanted to reduce, just to give you an example, I would reduce the 180 with the 6. I would reduce that first and then multiply, right? But I don't want to reduce first. I want to make this a little bit more challenging for everybody. So instead of reducing, we're going to multiply straight. 13 times 180 gives us a very ridiculous number. That number, ladies and gentlemen, is 2,340. And we keep the pi. Then we have 6 times pi, which is 6 pi. Okay, that one was easy. Now, remember we talked about earlier, things don't go away. They don't eliminate. They just transform. So anything over itself, what is that? If I had 5,262 over 5,262, that equals what? You should be yelling at me and saying 1, it equals 1. And if you said 1, that is correct. That means that elephant over elephant is equal to 1. Pryia over Pryia is equal to 1. And anything over itself is equal to 1. So here we have pi over pi. And we like that because that becomes 1, right? And it's the same as if you saw it over here. It doesn't eliminate, it just becomes a 1. And it's kind of like unconstitutional to say, to rewrite 1. 1 is 1, and we understand if I had 1 pi, it's the same as saying pi. So if I had 2,340 times 1, it's the same as saying 2,340, right? So that is the method that we apply here, that these don't necessarily eliminate, they do go away, but they become a 1. So now we're left with 2,340 divided by 6. That gives us a lovely numerical answer of 390 degrees. But why don't I like that answer? Can anybody tell me why I don't like that answer? It's a nice number, but it's not a great number. I don't like that number because it's past 360. We don't want it past 360. So something to keep in mind is when you're doing these and you get like a really large number, you want to start subtracting 360. Why do we subtract 360? 360 is the circle. Here's the circle, right? We know that a circle is 360 degrees. So if I start here and I go all the way around this way, I'm going to come right back to that circle. Then what's happening is I'm going how much more past the 360? That's the degree I need, because how are you going to draw 360 and whatever is left? You cannot draw that. So we have to keep subtracting the 360 till we get to anywhere between 0 and 360. Between. It could be 0. 0 just means no angle, just means flat, right? So keep in mind that when we're given those little things, that we have to always remember the little tidbits, right? So we're going to subtract our 360. We get 30. 30 degrees is the answer we're looking for here. So 13 pi over 6 becomes 30 degrees. That is our winner chicken dinner. All right, one more, and then move on to the next one. Ready? 4 pi over 7, we're going to multiply that by 180 over pi. So because we're a little bit wiser than the last problem, I'm going to cross off my pi's here, and now I'm only going to use my numbers. And 4 times 180 is 720. And 7 times 1 is 7. 7 goes into that number not an even amount of times. So if you have to use your calculator, use your calculator, or go off to the side and do some regular hand division, right? And the lovely number that you're going to get is 102.857 degrees. You can use 1, 2, or 3 decimal places. There is no rule here as to how many you need. And ta-da, we have gone from degrees to radians and radians to degrees. If you have a question, you know what to do, drop it in the chat. So, I was on Instagram the other day, and you would only believe, you probably would believe it, maybe not, I actually watch math videos. I enjoy watching math videos. So I actually watched somebody break down the unit circle in a way that I had never seen before. So I'm about to teach you guys a trick that I learned from somebody else, but it makes it so much easier for you. And I know sometimes you guys need the math circle, the unit circle. So let's talk about the different components of it really quick. We have a circle and it's broken into 4 sections, right? Our 4 sections here are the main sections. I call them the main sections because these are the major pieces that we don't really have to manipulate or figure out too much about. This is our 0 degrees. Oh, let me write it in black because it's in black. This is our 0 degrees. Then if we go up here, it's going to be our 90 degrees, our 180 degrees, and down here is 227. Right? So we have those. Then we know that on the unit circle, a regular typical unit circle, it's cosine and then sine, right? And we have our pieces. So this one is going to be 1, 0, 0, 1. This guy over here is negative 1, 0, and the guy down here is 0, negative 1. All right, a circle, we go out to ones, and then we just list the points, because it's as if we were on a coordinate plane. And if you can remember that, this will be a little bit easier, right? So that's pretty much all there is to know about those sections. So we move forward, and we take each section and we break it into half. Well, if we had 0, 90, I forget to write the degrees, 180, and 227, break that in half and we get what? You guys should be yelling at me, 45 degrees. So there's 45, and then we have 135, and we have, oh, that's not 227. You guys are letting me talk nonsense. I apologize. That's 270. Because 180 plus 90 is 270. I am so sorry. That's 270. So in between that would be 225. And in between this, because remember when we come back to 0, it's 360, right? So in between 270 and 360 would be 315. Okay, so now that we've broken it into halves, we're breaking it into sections because there's one more section left. The orange section. Okay, so we did the blue section. The blue section was taking each piece and breaking it into halves. And then now we're going to break them into thirds. All right. So now that we're breaking it into thirds, we're going to start again. 0, 90, 180, and not 227. It's 270. Because I have not completely lost my mind yet. It is 270. So now if we're breaking this into thirds, everyone knows their 3 times tables. So write out your 3 times tables. 0, 3, 6, 9, 12, 15, 18, 21, 24, 27, 30, 33, and now add your zeros. 0, 0, 0, 0, 0, 0, 0, 0. Okay, now that we have all of our degrees figured out, this is where it gets fun. Nope, I apologize. Hold on. I'm trying to switch the page. Here we go. We're going to combine them. I know, I'm absolutely crazy. This is like so much fun for me because I'm like, we are getting ready to do the big part, and you guys, your minds are going to be blown. Okay, so we start again with our base case, right? So this is how we should be doing it on our paper. We kind of like break it into our sections. So we start with our 0, 90. You guys are tired of hearing these numbers. 180, 270. Now we put in our 45. What did I say these numbers was? 45, 135, 225, and 315. Now I'm going to put in my 30s. So 3, 6, 9, 12, 15, 18, 21, 24, 27, 30, and 33. All right. You guys ready for the fun part? I know. You guys are like, this is not fun. I'm over here having the time of my life. All right. Now, most of you, if you guys have learned the unit circle, know that it is definitely a daunting task, right? It seems like you sit here and you're learning this thing forever. Well, I'm about to blow your mind. I know I keep saying it, I'm not showing you. I'm about to blow your mind. Here is the first quadrant, right? Quadrant 1. Let's go ahead and label that. Then this guy is quadrant 2. Because remember, we're looking at it as a coordinate plane. Quadrant 3. And then we have quadrant 4. Okay, are you guys ready? Here we go. I'm going to write my points with my lines and my commas and my parentheses and nothing else. I'm going to do those in black. There's my comma and my line, my comma and my line, my comma and my line. They look like weird faces. They're like closed eyes at you. All right. So anybody that has learned the unit circle knows that this is where we start writing square roots, 2s, 3s, 1s, all this good stuff. You are going to start with here. And in the, okay, so before we do that, I know, you guys are like, come on, just tell us. Every denominator is what number? Every denominator is 2. So you write 2 everywhere that there is a denominator. Okay, here we go. You guys ready? We are going to start at 30 degrees. And in the numerator, to the right-hand side, so our y value, or in this case, our sine value, I'm going to write 1, and I'm going to go upwards, 2, 3. I'm going to change the color. 1, 2, 3. And then when I get to the top, I've got to come back, right? So to come back, I'm going to go backwards. I'm going to start at the top and go 1, 2, 3. So 1, 2, 3. And then what am I going to do? This is my fun part. This is where it all just comes together. I'm going to put a radical sign on everything in the numerator. Radical, 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 radical. And we're almost done. Here's the best part. What is the radical of 1, or the square root of 1? It's just 1. So I'm going to delete that radical, and I'm going to delete that radical. And guess what? That is your unit circle. And it didn't take long at all. I know, it just kind of like we really broke down and we kind of went through it. But that's it. That's the whole unit circle. Because if you know this part, then guess what? You know the rest of it. And if it's a coordinate plane, you can put your negatives where you need to. And if you want me to finish it, it's okay. I will go ahead. Don't twist my arm or anything. All right. So what ends up happening is, let's use some colors here. This guy goes here. And this guy goes here. And this guy goes here. And it's the exact same thing, just change your negatives and positives. So what do I mean by that? Well, if it's 1/2 and square root of 3 over 2, if I'm in quadrant 2, my x values are negative. I should be hearing you yell, negative. It's negative, and my y values are positive. So negative 1/2 and radical 3 over 2. Then I'm going to do the next one, right? And my x values are negative, so negative on the outside, negative square root of 2 over 2, and square root of 2 over 2. And then the last one, negative square root of 3 over 2, and 1 over 2. Then I'm going to do quadrant 3. I'm going to keep my colors so you guys can see them. Oh no, I'm going to run out of space. That guy's going to go there. Okay, I'm coming down, and I'm going to have a negative and a negative. So negative and another negative. A negative and another negative. And the last one, a negative and another negative. I know, we're almost done. Okay. I really hope someone else is sharing this joy with me. All right, we're almost there. So this guy's gonna be green. This guy's going to be blue. And this guy's gonna be yellow. All right. And now we're in quadrant 4. So we're gonna be a negative and a positive. So a negative and a positive. A negative and a positive. And the last guy, a negative and a positive. And wham, bam, thank you, ma'am, we have a unit circle. I know, isn't this like fun and exciting? For those of you that need it, there you go. That's all you need. One quadrant, and you just have to remember 1, 2, 3 up on the right and 1, 2, 3 down on the left. Everything gets a denominator of 2. Put your radicals in, and boom, your unit circle is done. I know I couldn't not share that with you guys today. I've been like so excited to do Wednesday so I could do this with you. Okay, and we resume back to the questions, our regular programming. Number 2 says, find the reference number for t where it's equal to 2 pi over 3. Well, you can't answer the question unless you know what a reference number is. So does anyone by chance know what that is? What is a reference number? You can actually find it by looking on the unit circle. Look at unit circle. And if it's on the unit circle, where will it be located? It will be located straight across. Okay, so that's technically not the technical way to do things, right? That is the kind of like shortcut way. So if 2 pi over 3 was on the unit circle. Oh, we didn't do any of our pi's and stuff. I apologize. 2 pi over 3 is on the unit circle. We would just go to the unit circle and then go across from it, and we'd be able to grab that point. But we didn't do the radians. So you're looking at me like, okay, well, how are we supposed to do this problem if you're not giving us the information to do it? We're going to take this guy, and let's think about it really quick, right? If we're on a unit circle, and this guy is 0, and this guy is pi, across is pi, right? So when I go back to 0, that's 2 pi, and then I go to pi again, that's 3 pi, and we're kind of doing that thing, right, where we're going around, we're adding pi. Well, the same thing's going to happen here. If we're going across at 180 degrees, we're going to add pi. So technically, the technical way to do this is to add pi. So here's the technical way to do it, right? So to add pi, would I just get 3 pi over 3 to equal pi, and that's my answer? Oh no, it's not an answer choice. Did I do that right? I did not. Why can I not just get 3 pi and end with pi? Because I have a fraction, and you guys should be yelling at me. Tisk, Miss Pryia, you should have done it based on a fraction. Because we have fractions, so you have to add fractions. When you're adding fractions, there's a rule. What's the rule? Adding fractions, we always need common denominators. Yes, you should be yelling at me about that. So 2 pi over 3 and pi, there's only one denominator to figure out, right? Which is the best, because now we don't have to really multiply both. We can only multiply one and move forward. So to get pi to be a common denominator with 3, we're going to multiply pi by 3 over 3. And remember, anything that does not have a denominator is always over 1. Love the chat today, guys. Great job. So let's go ahead and we're going to add, we're not multiplying. We're going to add what we get here. Well, we multiply 3 and pi and we get 3 pi. And we multiply 3 and 1 and we get 3. And now we add our numerators and keep the denominator 5 pi over 3. C, winner, winner, chicken dinner. Add pi. That doesn't seem so bad. Okay, I know, I'm just all about the unit circle today. It is not a geometry question. This is a unit circle question, so it can fall under trig or pre-calc, even calculus, anything that technically displays the unit circle, because this is just knowledge of the unit circle, right? So if P is equal to this, and they tell us square root of 3 over 2, and they give us Y, and they tell us it's on the unit circle, and then here's the information that we need. It's in quadrant 3. 4. It's in quadrant 4. It's in quadrant 4. 4. They want to know what the Y coordinate is. So they want to know this guy, right? So how do we figure that guy out? Well, we go to the unit circle, and we don't go to the first, second, or third one. We go straight to the fourth one. So remember, the fourth one is the one down there. And we fill in what we know, right? So we know 0 is here, 270 is here. We know that we have our orange line, which is there and there. And we have our blue line, which is there. Our blue line is right in the middle at 315. Our orange line is 330 and 300. And we know what these coordinate points are already because we had already figured them out. So this one is 3 over 2 and negative half. This guy is square root of 2 over 2 and negative square root of 2 over 2. And that guy over there, 300 is half and negative square root of 3 over 2. So we're looking for something that's in relationship to this, and we need to just simply put in the Y value. So square root of 3 over 2 is at 330 degrees. The great thing there is we know that the Y coordinate or the sine coordinate is negative half. And that right there is our winner, winner, chicken dinner. And yes, the coordinate circle, the unit circle is as easy as using it like that. So I put the unit circle so I could draw it, but I drew it anyway. So this is a trigonometry question. And here, this might be the select all question, right? So they're going to tell you that select all that apply, or sometimes on the test, there's even a fill in the blank, right? Not all tests are like that, but some tests are. So this would be a select all that apply or a fill in the blank kind of thing. So we read the question that says, what are the 6 trigonometric values of t if cosine t is equal to negative 5 over 13 and the terminal point of t is in the quadrant 3? So it's good to know that we have quadrant 3, and it's good to know that we have this piece of information. Cosine of t is negative 5 over 3. Well, they tell us the 6 trigonometric values. Does anybody by chance know what they're talking about? Sine, cosine, tangent. Those are the 3 everyone seems to know. But what are the ones that coordinate to those? So for sine, we have cosecant. For cosine, we have secant, and for tangent, we have cotangent. So we should be looking for answers that are in relationship to these 6 that I just wrote out. Well, we're looking at this and we're going, okay, but how do I figure this out, right? Well, there is this really cool phrase that really helps us in any situation like this, and that happens to be SOHCAHTOA. Yeah, you're right, SOHCAHTOA. I know, I probably lost my mind at this point. SOHCAHTOA. So we have sine for opposite over hypotenuse, then cosine adjacent over hypotenuse, and tangent opposite over adjacent. So what do we do here? SOHCAHTOA gets applied and we can figure it out. So the great thing is they already told us what cosine was, right? So I'm going to draw my triangle in the 3rd quadrant. So if you had trouble figuring it out, remember this is quadrant 1, quadrant 2, quadrant 3, and quadrant 4. So we're going to draw a triangle there. What do I mean by drawing my triangle there? I'm going to start with what the quadrant looks like. So I'm going to draw the main part of my coordinate plane, which looks like this, right? That's the section of the quadrant. And then I'm going to connect it and call it my triangle. Boom, there's my triangle. Now remember, our 90-degree angle always goes there. It doesn't go anywhere else. And something to always remember is our hypotenuse is here. That is our hypotenuse, right? So we're going to put in the information that we know. We know cosine. We know cosine because they told us cosine. And we know cosine from SOHCAHTOA. So we know that the numerator is our adjacent value. And we know that our denominator is our hypotenuse. So based on this, wherever cosine of t is, we have a value that we can plug in. Well, 13 goes there, and it's -5. So here's the thing. Quadrant 3, when we look at our values, our x values are negative, and our y values going down are also negative. So the really cool thing here is it doesn't matter where you put the -5. Because it's a negative number, it can go in either position. So let's just put it at the top. And then we're going to technically be solving for that guy. Well, how do we solve for that guy, the question mark? I should hear you guys, and you guys should be yelling at me, Pythagorean theorem. Yes, we use Pythagorean theorem to solve any side of a right triangle that happens to be missing. So we'll have a squared plus b squared equals c squared. Remember, our a and b do not matter, but our c does, right? So a and b, so we'll start with -5 squared plus, we'll leave it x squared is equal to 13 squared. -5 squared is 25 plus x squared is equal to 169. Subtract 25 on both sides. X squared is equal to 144. And remember, we don't want x squared. We want x by itself, right? Because we're just looking for the side, not it squared. So we take the square root of both sides, and we get x is equal to plus or minus 12. Don't forget the plus or minus. This is where it's important to know what quadrant you're in, right? Because now that we know where we are, we know which number to use. Why do I say that? It would not make sense to use a plus 12 here because this is the 3rd quadrant and that side has to be a negative number. So I'm going to insert my -12 as that side. All right, now, remember we put -5 at the top, which told us that -5 is adjacent to the T angle. So that tells us that our T angle had to be where? There. because that means it's now adjacent. So just to fill in the triangle, that is the rest of the triangle. That angle we do not know. It is not important to us. But we still need to put in the sine, cosine, tangent, cosecant, secant, and cotangent information. And we're about to do that right down the middle. Okay, so let's start with cosine. Cosine, we know, well, cosine of t is equal to -5 over 13. We know that from what they told us. We know that the inverse of cosine is secant. So secant is going to be the inverse of whatever the reciprocal of the -5 over 13. So -13 over 5, right? And then sine is opposite over hypotenuse. So our opposite angle is -12, right? Our opposite from our opposite side, not angle, opposite side from our T angle is -12. We'll have -12 over our hypotenuse, which is 13. And on the contrary, we'll have cosecant is equal to -13 over 12. Then we have cotangent, which is opposite over adjacent. So opposite is -12 over -5, which ends up being 12 over 5. Negative over a negative is a positive, don't forget. So on the contrary, oh, I wrote the wrong one. I'm sorry, that was supposed to say tangent. Brain boo-boo. Tangent, tangent. Tangent of t is opposite over adjacent, and that is 12 over 5, because negative over negative is a positive. And our cotangent is the reciprocal, 5 over 12. And those would be the 6 answers that you would choose from, right? You wouldn't choose anything else. You want to make sure that your numbers match up and they match up to the trig value that you've been asked to identify. They don't seem so bad once you actually start doing them. And I'm all sorts of crazy today. You know what to do. If you have a question, drop it in the chat. So sometimes they ask us to condense, rewrite, expand, solve, right? All those things kind of mean the same thing. It's to change the form based on what we already have. And if you know your properties of your logarithms, right, you'll be able to do this. So we have to know a few things. These are not answer choices, these are questions. We have to know a few things in order to move forward here, right? We have to know what our log properties are. Well, I'll give you a hint. To rewrite these, we're going to want to write them kind of either as a sum or a difference, something like that. Because we have right now something that's being multiplied, divided, and I don't know what C is telling me yet, but we know that it's there. So if we have to move forward, okay, I'm going to come back to that question. That's a really good question. If we have to move forward, we go, all right, well, for the properties of what I have, to rewrite a log that's being multiplied, I'm going to rewrite it as addition. So what do I mean by that? I have to take each individual piece of the multiplication and write it as an addition. So I'm going to have log of 4 plus log of x squared plus log of z. Then you can do one more thing, just in case that's not an answer choice. Sometimes they like to bring that exponent out to the front, and that's just another way to rewrite it. So we'll have log of 4 plus 2 log of x plus log of z. And either one of those would be our answer choice here. So if we add for multiplication, can you take a guess of what we're going to do if we're dividing? The really great thing about the division bar, that fraction line, it looks like a big subtraction sign, right? So we're going to subtract here. and we're going to subtract the numerator from the denominator. So now we're going to have log of x4 y7 minus log of z. But remember, we rewrote our multiplication earlier, so we're going to want to expand that first term. And we're going to add that. Now we're going to have log of x to the fourth plus log of y to the seventh minus log of z. And then just in case we needed to, we're going to bring our exponents down. So we're going to have 4 log of x plus 7 log of y minus log of z. All right, and then we have one more here, and then we'll go back to the last question because we have some questions on them. Well, I have log base 2. So one quick thing to always remember is if you don't see an actual log number base, a log base number, that's that 2 there. If you don't have one, what is the automatic understood log base that we should always have? It's always going to be a 10, right? So if you don't see a number, it's automatically going to be 10. So if for whatever reason this said log of 8 is equal to x, we know that a 10 should be there, right? So that's just little things to always keep in mind about stuff that we know. So it's going to be a log base 10 of 8 is equal to x. That's if we didn't have a number there. So now I have to rewrite this, and I'm going to rewrite it in exponential form. What does that even mean? It means that we rewrite how it looks based on an exponential looking equation, right? So my base number is going to be my base number for my exponent. Cool how that worked out, right? I'm going to have 2 and bring my x to the numerator and say it's equal to 8. Right, so our base 2 from our log is also our base and our exponent. So that's our 2. We bring the answer over to the exponent and we say that it's equal to 8 because 8 is over there. Well, 2 to the what power is equal to 8? 3. I almost didn't have enough fingers. 3. 2 to the third power, so x is equal to 3. I can show you 2 times 2 is 4 times 2 is 8. 1, 2, 3. All right, so I was asked a really great question about the last one. How do I solve a problem like this on a timed test? It's not as much work as it may seem when we're talking about it together, right? Because remember, I'm going through all the steps and making sure that everybody's on the same page. If you were to solve this by yourself, it shouldn't take you more than 3 to 4 minutes to really get through it, right? And that's if you're kind of taking your time. If you're kind of going quickly, you already know what there is to expect. You should be able to spit out the sine, cosine, and tangent, spit out SOHCAHTOA, know that the inverse functions from sine, cosine, and tangent are cosecant, secant, and cotangent. They will give you the inverses of whatever you end up with numerically. Be able to draw your shape, find the side, and then plug it all in. It's not that much work when you're doing it by yourself, but it seems harder when we're doing it together, only because we're taking a little bit longer to get through it. But the key thing here is when you're doing questions like this on your exam, it's to make sure you're picking up those key pieces, right? So quadrant 3 was a really big piece here. If we had missed that, let me show you what that would have looked like. We would have ended up drawing our triangle in quadrant 1 because that's our base case scenario. We would have put our part there. We would have had -5, 13, -12. Yes, by default, you drew a triangle, but it is not represented in the quadrant 1. it's not represented in quadrant 1 because the y should be positive and the x should also be positive, right? Sometimes it's about making sure that you're understanding what your numbers need to be. When we solve to get this negative 12, remember we got plus or minus 12. If we needed this to make sense, we needed to know what quadrant we were in. We couldn't have figured out it was 12 or negative 12 without knowing where we needed to be, right? So it's about being able to pick out the little pieces of information that they give you in order to move forward. When you stare at this question, you see 6 trigonometric values. Some people automatically shut off. That's okay. But when you see cosine of t is equal to negative 5 over 13, and they don't give you anything else, you should always be thinking SOHCAHTOA. Those are my sides because they're giving me a cosine. And the only things that I know about cosine are I can use the cosine in SOHCAHTOA, I can use the cosine law, and that's pretty much it. That's all there is to it. But in order to use the cosine law, you need an angle, and we don't have any angles here, right? So it's about making sure that you're using the formulas that you know to move forward. If you see that a formula doesn't make sense or you don't know how to apply it, I would suggest skipping it, right? And we knew that we needed to solve for the last side because we didn't have anything else to use. We know that SOHCAHTOA is all about all the sides of the right triangle, and we only had 2 out of 3 of them. So there was a missing piece that we had to solve for. And if you look at the calculations, we haven't really done anything past Algebra 1 other than know our trig functions and know how to apply them. All we're doing is plugging them in. We're not necessarily even solving with them. This is more basic knowledge of what the trig values are, not necessarily applying our trig functions. So these are definitely doable in that time setting. It's just making sure that you can identify the problem as quickly as possible in order to move forward. So like I said, when it comes to equations, if you don't know what you're using, I always suggest writing them out. What do I know about cosine? I know what about cosine? I know that cosine squared plus sine squared is equal to 1. Okay, that doesn't help. What else do I know about cosine? I know that I have a cosine law that tells me a squared is equal to b squared plus c squared plus, minus 2ab cosine of big A. Sometimes that's written as alpha. I know that. Okay, well, none of that stuff's helping me. So what else do I know about cosine? Well, I know cosine's related to SOHCAHTOA. And sometimes just jotting that information down really gets your gears turning, and it really helps you figure out how to, get to that solving part of the problem. That's a really great question, Tom. Thanks for asking. Well, we're almost out of time, so I'm going to skip through really quick to the end because I love to say thank you. I love to say thanks for showing up. I love the participation that you guys have, and I wish you all the best. You know where to find us. It is thelearningliaison.com. We have our online tutoring options. We have our one-to-one tutoring options. We have our workshops, and we have our boot camps. We are here for you, anything you need. Until next time, everyone. Bye.